Welcome to week 4, module 4 for ME 270 structural dynamics. So this week we'll begin the study of forced motion by looking at the response of undamped and viscous damped single degree of freedom systems to harmonic excitation, and specific sinusoidal. So a couple key points here for this week. Reminder, your homework 2 is now going to be assigned, and this will be due on the 28th by 11 p.m. So this is your second homework assignment. Also, please reference back to the homework guidelines for details on format, grading, how to submit this. So you should be fairly familiar with this by now. You've already turned in one homework assignment. We've gone through it several times, and this will be the same format that we will be using for exam 1, which is coming up in a couple weeks. The other note here is quiz 4 has been posted to Blackboard. This will be due on Friday the 25th by 4 p.m. So these quizzes are just meant as basic concept reading quizzes. As long as you're going through your books, your lecture notes, you should be doing just fine on these. It's more to encourage you to keep up with your reading assignments and the materials with this online format. So if you do have any questions specific to things, reminder, I do have office hours on Tuesdays and Wednesday mornings from 9:30 to 10:30 a.m. I'm also around throughout the entire week. I have teams set up on my phone and my home computer. So if you have any questions related to material, homeworks, quizzes, anything at all, please feel free to reach out. Even if it's not during my normal office hours, send me an email or a message, and I'll make sure to set up a time that we can get together. So in chapter 4, dealing with response of single degree of freedom systems to harmonic excitation, we have a couple things that we want to be able to accomplish by the end of this. So we're going to take a look here. First bullet, steady state response and total response of undamped single degree of freedom systems. Second, look at steady state response and total response to viscous damped single degree of freedom systems. Again, both of these are subjected to harmonic excitation. We're going to be able to describe the effect of the damping factor and frequency ratio on amplitude and phase of the steady state response of these viscous damped single degree of freedom systems subjected to this same harmonic excitation force. Sketch for various frequency ratios, plotting, polygons. So this is where we're going to introduce either Excel, MATLAB, Python, whatever you want to do in order to actually graph these out. Use complex frequency response method to obtain expressions for the amplitude and phase of the steady state responses to a viscous damped single degree of freedom system. Set up the equation of motion for base excitation problem and obtain steady state solutions, frequency response functions for absolute motion and motion of mass relative to the base. Work on some numerical values here for magnification factor. Discuss the principle of operation of seismic transducers, vibrometers, accelerometers. Look at frequency response data and calculate work done per cycle of harmonic motion. So these are the main goals of the chapter. I know this is a lot. We're going to focus on the top ones of these primarily. Your readings will cover the last 2 or 3 of those a little bit more than the example problems we'll do in class. So this 4th module is going to be broken down into 3 different sections. First section is going to be module 4-1, looking at this harmonic excitation. So we're going to look at the response of undamped single degree of freedom systems to that harmonic excitation. We're also going to look at the response of viscous damped single degree of freedom systems to the same harmonic excitation, looking at frequency response functions. So one of these examples that we're going to look at in class and go through a couple example problems in my video solutions is a simple spring mass system. I think this is a great system to reference back to. It's relatively simple. We just got a mass, a spring, an external load, and some displacement here. And we can start applying new concepts and new terms to the same type of system and expand upon it. So what we have here is we have an externally applied load, our P of T. So we have our P of T over here, our externally applied load. We have our equation of motion, so we can reference back to equation 1-4 on page 9 of our textbook when we're talking about equation of motions, where we have this function right here. Our mu double dot plus ku is equal to pt. Now, when we're talking about these equations, our diagrams, we want to remember we have all of these different variables here, and this is where on our setup pages we're solving these out, we want to plug these in. So m is our mass, k is our stiffness, u double dot is our acceleration, second time derivative of our position. There we go, our position, our u displacement, and P of T is this external force. So this is a great slide to reference back to as we're going through some of these example problems, or if you're reading through the chapter and looking back at some of the problems that they're working on. So as we get a little further into the spring mass system, a couple other things that we're going to need. A lot of times we're going to need this ratio here, our R, our frequency ratio. So this right here takes our omega over our natural frequency omega sub n. So that's one that we really want to make sure we reference back to. We're going to use this a lot in example problems, and I reference back to where we get that from in our text as well. Our excitation frequency is equal to the natural frequency here, so different ways they may word things in the problem that we need to be aware of and understand which terms and which variables we're going to use. And a condition called resonance here, where R here is our frequency ratio that we talked about above. Our omega term here is going to be our forcing frequency in units of radians per second, and our omega sub n here is going to be our natural frequency right there. So another thing that we want to keep track of as we're going through these problems is our units. Are we dealing with hertz? Are we dealing with radians per second? All of those things become important. And also, as we're doing that, a double check, doing this ratio out, it should be unitless. So these should both have the same units when we're plugging in, searching for our R, our frequency ratio. So in module 4.2, what we're going to look at here now is complex frequency response and some vibration isolation, looking at force transmissibility and base motion. Lastly, we're going to move on to 4.3, and really in 4.3 all I'm doing here is introducing a little bit more with some of the measuring vibration instruments, but more than that, going through, I've posted a lot of good practice problems. A lot of this chapter, there's not a ton of new concepts. There's a couple new equations and things like that, but it's more tweaking them and how to apply them to various applications and various problems. So for this here, I have a bunch of different practice problems going through and using those key equations so you can see how things will vary slightly as we change our problem statement, what they've given us, and what they're asking us to solve for.